Now we can talk about magnetic domains. Magnetic domains are what make permanent magnets, and without them, we would have no permanent magnets. It's present in all materials which are ferromagnetic. We have to start with understanding that every electron spins. Now, if you talk to a quantum mechanic, they'll say, well, it really doesn't spin, but it sure acts like it's spinning. So we can just use this assumption of classical mechanics that the electron is spinning and to figure out what its magnetic field looks like. So let's take a look at this electron first on the left. And if you use your coil right-hand rule, we can figure out which end of this spinning electron is the north magnetic pole. So you've got to use the left-hand rule because it's an electron. And you can see that in this situation, on your left, it's curling into the page. It's like a spinning electron. This is the way it's spinning. Use the left-hand rule. And on your right, it's going out of the page. So by curling your fingers around like this in the direction of the spin of the electron, you can see that the north pole of this electron is towards the top and the south pole is towards the bottom. The other electron, this one on the right by contrast, that is spinning the other way. On your left, it's going out of the page, and on the right, it's going into the page. So that, using the left-hand rule, is pointing down. Again, we use the left-hand rule because it's a negative charge spinning around. So that'll give us the north pole down and the south pole up. If you draw your magnetic field lines in like this, it comes out of the north end, but then immediately goes into the south end of this one, comes back out there and curls back around. So it's forming a closed loop that's like this, which effectively cancel each other's B field. It keeps the magnetic field lines in a really tight loop right there. If you have paired electrons, you don't really have a strong B field. You have basically nothing because they cancel each other's B field. However, in iron and other ferromagnetic materials, several suborbitals have unpaired electrons. Here's an example. Now, you may have done this in chemistry where you do these little up and down arrows. What you were actually drawing, although you probably didn't know it, was the magnetic polarity of those electrons. For example, in iron, we have an argon core, but then we add 4s2 and 3d6. So that means that all you got to do is you first fill in the 4s shell. Spin up, the north pole of that electronic magnet is pointed up, and spin down, so we fill those in first. Then we start filling in the 3d orbital with ups. Spin up, north pole up, north pole up, north pole up, 4 and 5, but then we have another one that we have to do spin down right there. So you will notice that several of these electrons are unpaired. All these right over there have no pair. So every atom is a magnet. Every single atom of iron is a magnet. Now, any material that's got unpaired electrons exhibits what's called paramagnetism, which is a weak magnetic effect, but certain things like iron, nickel, and cobalt have ferromagnetism, which is an even more powerful magnetism, and it has to do with what we're talking about now, domains. Now, in most materials, atomic magnets are aligned randomly. And that's what happens in paramagnetism. Every atom is a magnet, but if it's got unpaired orbitals, but they tend to align randomly, creating a net B field of 0. Now, due to quantum mechanical interactions, some materials, nickel, iron, and cobalt to be specific, are ferromagnetic materials, and what they have is billions of neighboring atoms which tend to have their unpaired electrons aligned in the same direction. A group of billions of aligned adjacent atoms that are atomic magnets is called a magnetic domain. And in this picture right here, every one of these sections here is a magnetic domain. Each one of these sections has billions of aligned atomic magnets. I'm outlining the domains. Now, each one of these arrows, each one of these individual arrows, like this one and that one, those each represent billions of atoms. So we're talking about many billions of atoms. This drawing right here has 9 different domains, and each arrow in that domain represents billions of atoms. So a group of billions of atoms that are aligned magnetically, they are aligned adjacent atomic magnets, is called a magnetic domain. So here's another domain, here's another domain, here's another domain. So you can see these domains. Now these are visible under a microscope. They're typically like 1 to 100 micrometers across. Here's a picture right here. This right here is an actual picture. What you see as a different color right in there, that is all one domain right in there. And you have another domain right here, and it's kind of shaped like that. And here's another domain right there. Anywhere you see a different color, that's a domain, a section of atomic magnets that are all aligned the same way. So that's what we're looking at right there. And this length right there is 10 micrometers, so you can see how big the domains are. Unmagnetized ferromagnetic materials, they do have domains, but the domains are aligned randomly. In other words, let's draw a picture of this. For example, here's unmagnetized iron. You might have a domain pointing that way, you might have a domain pointing that way, one this way, one this way, one this way, one this way, and they're totally random. Now, within each domain, now what I'm doing here is I'm representing every domain with one arrow, showing how the billions of magnets are atomic magnets are aligned. Here in this picture up here, every arrow represents billions of atoms. In this picture right here, every arrow represents a single domain with its atomic magnets aligned in the direction shown here. So what you do is if you put a ferromagnetic material in a strong external B field, that aligns the domains in the same direction. And many will remain aligned even after the external B field is removed. Here's a really cool applet that shows exactly that. So what we have here is a ferromagnetic material, and this represents the alignment or the orientation of each of the domains. Notice they're aligned very randomly. What I'm going to do is I'm going to take this bar magnet, which will provide an external magnetic field to this ferromagnetic material. I'm going to move the bar magnet close. Watch what happens to the alignment of those domains when I bring this close. Notice that they're starting to spin. And really what happens is the domains that are aligned with it actually become bigger. They absorb more atoms at their edges. And the domains that are not aligned get smaller. But what you end up with is the same thing in either situation. All these domains are aligning with this external magnetic field. And even when I pull away the permanent magnet, those domains stay aligned. So now what I have right here, this thing is now a new permanent magnet. Now if I shake or heat this ferromagnetic material, or slam it really on the ground, or heat it to what is called the Curie temperature, those get re-randomized and it goes back to that. So that is how you make and then break a permanent magnet. So here's our magnetized iron. If they are all lined up, and they're never lined up perfectly, but they all tend to line up in the same direction, and that is a magnetized piece of iron with all the domains relatively in the same direction. As I mentioned, heating or hitting a magnet on the ground or on something solid will re-randomize the domains. And if you put a ferromagnetic material in the core of an electromagnet, it greatly increases the strength of the magnet, since it's like adding billions of aligned magnets to the electromagnet. So putting an iron core inside the electromagnet can make it thousands of times stronger, because you're adding thousands or even millions or billions of little atomic magnets that are all lined in the same direction.